Hello, we're going to talk about gases today, and you're going to fill in your notes here. Gas pressure, you've already done the gizmos, the gas pressure, you know some of the relationships, but let's define a few of these things. First of all, what is pressure? Pressure is the force that is exerted per unit area by gas molecules as they strike surfaces around them. All around the room, we've got particles hitting against the sides of the walls, and that force is what we call pressure. If we were to evacuate the air from this room, there wouldn't be that force pushing out on the walls, and the room might collapse because of lack of pressure. Just as a ball exerts a force when it bounces against a wall, a gaseous atom or molecule exerts a force when it collides with the surface. And this is a big physics concept, but we don't have to worry about it in chemistry. All right, now, the molecular collisions. Gas pressure is a result of the constant movement of gas molecules and their collisions. All right, gas particles are in constant motion. And that's pretty much the definition of gases, that they are not attracted to each other for the most part, unless it's high pressure or low temperature. But they're in constant movement around them. And there's a couple things that will affect that. First of all, the number of gas particles. All right, if you put more gas into a container, it's going to be under higher pressure. All right. If your body is used to pressure pushing on it, if I were to take you out into outer space, your body would not have that pressure pushing on it unless you were in a pressurized suit, and you wouldn't necessarily explode, but your veins would burst and things like that. There are videos of people bringing up organisms from the bottom of the ocean, and when they bring those organisms up to the surface, because the pressure at the bottom of the ocean is so great, they have done all sorts of things, like their parts have exploded and pushed out because of that lack of pressure. All right, the second thing that would affect it would be the volume of the container. If you make a container smaller, that's one of the things you saw, as you make a container smaller, the pressure inside that container goes up. And then the third thing is the average speed of the gas particles. The faster the gas particles are going, the higher the temperature. Temperature is the measure of that kinetic energy. And so temperature and gas velocity is directly related. Total pressure exerted by a gas depends on several factors, including concentration of gas molecules. And here's an example of concentration. Here's a low concentration, here's high concentration. As volume increases, the concentration will decrease, which will cause the pressure to go down. Again, Boyle's law. This in turn results in fewer molecular collisions, which results in lower pressure. Gas pressure and particle density. Pressure exerted by a gas is dependent on the number of gas particles in a given volume. The fewer the gas particles, the lower the force per unit area and the lower the pressure. So a low density of gas particles is low pressure. High density is high pressure. All right. The next page is the barometer. A barometer is actually something you have all heard of, you just may not realize it. Anytime you hear the weatherman talk about pressure is falling, pressure is increasing, decreasing, what they're talking about is a barometer. A barometer is sensitive to the air above it. Normal pressure at sea level is 1 atmosphere, or 760 millimeters of mercury. And if that pressure increases, if there's more air that's pushing down, as it pushes down here, it would cause the mercury inside of a mercury barometer to go up. That's when the weatherman might say the mercury is rising, and that means it's higher pressure. If the mercury is falling, it's lower pressure. So let's watch this little video about So now we've seen what a barometer is and a little bit about the history of a barometer. Some of the different units we use to measure pressure, one is pascals. A pascal is 1 Newton per square meter. A Newton is the energy it takes to accelerate a mass that is 1 kilogram by 1 meter per second, that velocity increasing every second. So you're accelerating it 1 meter per second every second. And that's what a Newton is. The abbreviation is PA. The air pressure at sea level is 101,325. Pounds per square inch, you guys have all heard of. You've used it with your car if you've had to check gas tire pressure. Right now, everybody's tire pressure is probably a little low because the cold weather causes those particles to contract inward. That's Charles' law, volume over temperature. So you may have a low gas pressure reading in the winter, and then in the summer you may have to let gas out because if you filled it in the winter, as the roads warm up, the gas takes up more space, Charles' law, and expands, and so you would need to let some of that pressure out. A torr is another measurement. 1 torr is equal to 1 millimeter of mercury. So 760 torr is the same as 760 millimeters of mercury. Name for torricelli. Inches of mercury, of course we're in America so we use inches of mercury, but same concept. You've got that column that is about 1 meter high, and average air pressure around here is usually around 29 to 30 inches of mercury. Atmospheric pressure, we use atmospheres also. 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 29.92 inches of mercury, which is equal to 101.325 kilopascals. Okay? All right. All right, so the simple gas laws are what the book calls Boyle's law, Charles' law, and all those guys. And the 4 basic properties of the gases are pressure, volume, temperature, and amount of particles, which is, of course, moles. So the first simple gas law is Boyle's law. We already talked about this. This is an inverse relationship between volume and pressure. There's only one blank there, just because I put the picture in, it looks like it's 2 blanks. So here you've got a picture of a J tube, and we've got mercury in there, and we have this amount of space. If we increase the pressure by adding more mercury, that's going to force that space to get smaller, and so that will increase our pressure. And here's a picture of the graph that we've already done in our gizmo. Here, this piece we didn't do in the gizmo. What I want to do is I want you to draw a picture of what's happening to the gas particles. And what that looks like is right here. All right. In the first picture, the volume is 1 liter and the pressure is 1 kilogram. That's the weight that's on there. But what I want you to notice is that your gas particles are much closer together in the second one. So we'll draw our gas particles, and we're going to put arrows on them to show that they're moving. So then you'll draw the particles in the smaller space, but because it's less space, they collide more frequently, which I didn't do a very good job showing them colliding. But they're going to collide more frequently, which will increase the pressure. All right, Charles' law. Oh, we forgot to put this in. Back up here, next to this graph, remember that pressure times volume is inverse. So if we multiply them together, we get that constant. Well, when we looked at the gizmo, we saw that if we doubled the pressure, the volume would be cut in half. So we can call that constant the a second set of circumstances. So if this is the pressure and volume of the gas in the first set of circumstances, that pressure times that volume will be equal to the pressure times the volume in the second set of circumstances. And then we can solve for a missing variable. Charles' law is a direct relationship. And we have to make sure our temperature is always in Kelvin. All right, 0 Kelvin is also called absolute zero. If you were to take a gas and compress it down so that its volume was extremely tiny, the temperature of that gas at that very tiny point should be 0. That's why we can't use negative numbers. All right, and here you can see if we extrapolate whatever gas this is, the number of particles in there is 1.0 moles, and we have 1 atmosphere. If we continue to cool it off, you can see that the volume declines until all of these guys would reach the same point, which is now defined as absolute zero, negative 273.15. Okay, what's going on in our particles? Well, the temperature's making the particles move faster. So we can draw our arrows, but in the bigger balloon, here, let me find the picture for you. You can see that the speed shown by the tail, and I'm using an arrow to show it, the speed is much greater. So I'm using an arrow. But that hot air, that hot gas, the particles are going to move faster, because that is literally the definition of temperature, is how fast the particles are moving. Okay, if we move a water balloon from ice water to a boiling water bath, the volume expands. This is something you could do at home. The third law, oh, did we do the relationship? Let's put this back up here. Volume is directly related to temperature. And so if you've got a gas and you change its volume, you can figure out what its temperature is going to be by plugging in numbers into those values. Gay-Lussac's law is dealing with pressure and temperature. Pressure is to temperature, as it's a direct relationship. So if you've got a gas at a certain pressure and temperature, if you change either the pressure or the temperature, the other will change in kind, and you would use that formula. Our last example is Avogadro's law. And here we have volume is directly proportionate to the number of gas particles. Well, that makes sense. When you put more air into a balloon, the balloon expands. You get a larger air. So the more particles you have, the more, the larger the volume is going to be. If you have a gas at constant temperature and pressure, so if you increase the amount of gas in a sample, the pressure will increase because you're putting more particles in there. It's just like if you put people in a room and you keep putting more people in the room, the pressure doesn't increase, but your people are bumping into each other more. All right, so we can put this all together. So we know that Boyle's law is P times V equals constant. Charles' law is V over T. Avogadro's law is V over N. And Gay-Lussac's law is P over T. So we can put that together, PV over NT. So here is Boyle's law. There's Charles' law. There's Avogadro's law. And there's Gay-Lussac's law. And we can solve for our constant, which we did together. And that constant is what we call the ideal gas constant. The ideal gas constant is determined by the one you use is determined by pressure and volume. We're going to use the ideal gas constant that goes with atmospheres and well, atmospheres is the one we're going to use. So the one you're going to see is this one. You might see this guy pop up in a the online program, Mastering Chemistry, but not probably too much. Okay, finishing up here. Standard conditions. We want something to compare to, and so a lot of times we scientists set standards that are something that you can compare to. Standard temperature is the temperature at 0 degrees Celsius or 273 Kelvin. Standard pressure is 1 atmosphere, and we abbreviate this STP. So if I tell you you have a gas at STP, you know the pressure is going to be 1 atmosphere, and you know the temperature is going to be 273 Kelvin. Okay? If we substitute this information in, so if we say, okay, I have 1 mole of particles, and the gas constant 0.0821, and this is a 1 mole, and the units for this guy are liter atmospheres over mole Kelvin, and our temperature is 273 Kelvin, and our pressure is 1 atmosphere. Our units cancel so beautifully here that we're going to be left with liters. And when we do that math out, we get the answer, 22.4 liters. And this is what we call the molar volume. And that's where we're going to put, what we are going to put, see here, I did the math for you. So we're going to put that into our mole map up here into the top left corner. At STP, if you know the number of moles that you have, you can figure out the volume of gas by multiplying moles times 22.4 liters per mole. Same token, if you know the volume and you want to know moles, and it's at STP, you can divide by 22.4 liters per mole. This is true no matter what gas you have. If you have helium at 1 atmosphere pressure, at 0 degrees Celsius, 273 Kelvin, 1 mole will take up 22.4 liters, no matter what it is, helium or xenon or methane gas. They all are going to take up the same volume at similar, at the same conditions. That is different from when we are trying to calculate things like the mass using the molar mass, because your masses aren't all equal. All right, that's where we're stopping for today.